Good morning, everyone. Good morning, everyone. I'm Yu Zifeng. Today is our great honor to have Dr. Robert Rogers to give a talk today. We all know that Dr. Robert Rogers is a famous scientist in the typhoon community. He has made a lot of contribution to the typhoon observation and the research, especially in the mechanism. So in the past talk, he has given us a review about the typhoon observation experiments and the research advances. So today, he will continue to give us a report on the past, future, and plans of typhoon observation. So now, let's welcome Dr. Robert Rogers with applause.
Thank you. Deshay. Thanks, Dr. Yu, and welcome everyone. I'm happy to see some people here this morning. I know that there are a few of you that are out in the field right now, actually flying or planning to fly Typhoon Trami. So it's very fitting that I'm talking a bit about some of the experiences that I've had conducting field campaigns, observational field campaigns with aircraft as part of my past experience working for NOAA in the United States. So I'm going to talk a bit about what we did within NOAA to develop a field campaign and execute that field campaign, and what sort of the plans are currently, and then I think what could happen perhaps here in the West Pacific, hopefully using some of the lessons from my experience in the Atlantic. So just a brief outline. First, I want to start by talking about, I probably don't need to convince you of this, but to talk about why field campaigns are important, and then give just a quick brief summary of the recent NOAA field campaigns that I'm going to use as sort of a basis for what I want to talk about today, and maybe how it can be applied to a field campaign in the West Pacific, led, I guess, largely by APTCRC. So I'll talk first about some of the steps that went into developing the NOAA field campaigns that have been going on for about the past 20 years or so. And then using some of those steps to see how that could perhaps apply to a field campaign here in the West Pacific, building upon the successes of Exotica and Exotica 2. And then finally, just to using some of those lessons, perhaps I just have a proposed sort of field campaign and motivation for that field campaign that I'll present. Just something that is a proposal at this point, but obviously we'll have worked through that and perhaps refine that. So first, why are field campaigns important? Well, it comes down to observations, right? And really observations, I talked about this a couple of weeks ago as well, but observations are really an important part of what I would say is a balanced approach, using observations and modeling, numerical modeling and theory toward advancing our understanding and improving the forecasts of tropical cyclones. Observations can also provide real-time information on TCs. They can also allow us to perform or assess the performance of models. How well are the models doing? Where are they failing? Where are they doing well? How can they be improved? And finally, they can also provide a check on theories. Now, there are three primary observational platform types: airborne, spaceborne, and land-based. So I'm going to talk mostly about the airborne, but certainly the land-based is a big part of what I think happens here in China. And obviously spaceborne is, a crucial part of that because it can fill a lot of gaps that the aircraft and obviously the land-based cannot fill. Field campaigns, I would say, provide the opportunity to collect unique observations that can advance both research and operations, the forecast. And really that's, I think, what should drive a lot of what we want to do here in the West Pacific in terms of a field campaign. So what are some of the recent NOAA field campaigns? Again, I talked about this 2 weeks ago, so I'm not going to go into a lot of detail, but just a summary. Back in 2005, the emphasis for the field projects that were run in NOAA shifted from focusing only on physical understanding toward supporting operations and ultimately improving the forecasts. And at the time, and I'll talk about this in a minute, the big challenge was predicting hurricane, in this case, intensity. So we developed an experiment called the intensity forecasting experiment. So I wrote a paper that was submitted in the AMS bulletin back in 2006 that summarized that experiment, and then a follow-on progress report a few years later. And then a couple of years back, we shifted our emphasis from focusing only on intensity forecasting to broadening it to include all hazards, which again, I'll talk about a little bit more. And so that was a paper that came out a couple of years ago in the same journal. But again, like I said, these campaigns, IFEX and AFEX, are targeted towards specific operational goals, in this case, forecast improvement, or improving our ability to monitor tropical cyclone or hurricane structure and intensity. In a sense, they're different from other field campaigns that happened in the US that did target specific physical processes, such as the NASA Convection and Moisture Experiment, the NSF RAIN-X, rain band experiment, and PREDICT, which focused on tropical cyclogenesis, the ONR, Office of Naval Research, Tropical Cyclone Rapid Intensification Experiment. So those had specific physical processes that they were targeting. IFEX and AFEX were a broader umbrella that incorporated physical processes into a broader effort to improve forecasts. So again, physical process research still does play an important role in these NOAA campaigns, but it's not the only game in town, so to speak. It's not the only motivation for doing these field projects. So, I think, and I'll show you this a little bit later too, I think those AFEX and IFEX, certainly IFEX, have been successful, and I'll show you why in a few slides. But, in my experience, at least, there are several steps that went into these field campaigns, and they all needed to be satisfied, I think, in order to have what I would say is a successful field campaign. So I'm just giving you my lessons in the case of IFEX and AFEX in some sense, and perhaps those can be applied here in the West Pacific. So, the first step I would say is you have to identify your stakeholders. And what is a stakeholder? A stakeholder is someone who has a specific interest in whatever it is that you're doing, and it's someone that you're ultimately serving in your experiment. So it could be any group of people, and I'll talk about this on the next slide. But you definitely need to know who it is why are you doing this? Who are you doing it for? Are you doing it for the government? Are you doing it for the private sector, or whatever? And what are their needs? And so ultimately, how can you address those needs? Once you identify their needs, you need to design an experiment. So, in the case of IFEX, we designed that experiment to ultimately address the needs of the stakeholders, which I'll talk about. And then with that experiment design, you have to develop a plan. So how are you actually going to tackle that problem? How are you going to test those hypotheses that are part of your experiment? What are the logistical concerns and things like that? All of that goes into the plan that you have to develop. Obviously, you have to execute the plan. So you're seeing an example of that today. There's missions that are going to happen in Trami, I think, tomorrow. So, that's an example of executing that plan, and that has to be done effectively. And then the very important part as well is after everything's done, you have to go back and assess how successful were you. Talk to your stakeholders. Are their needs being met? How can you improve what you're doing to better meet their needs? And ultimately, those 5 steps, or at least what I've experienced, in my experience, are the keys to really having a successful field campaign. So I'm going to go a little bit more detail into each of these in the case of IFEX to talk about how we did it, and then perhaps how it can be applied in the West Pacific. So that's exactly what I wrote here. Okay, so going back to that first step, so identify your stakeholders and what are their needs. So what are some examples of stakeholders? Well, I could think of 4 off the top of my head. First one being the operational centers, the forecast centers. So in the case of IFEX, it's the National Hurricane Center. They're the ones that produce the forecasts. It's the Environmental Modeling Center. That's the NOAA center that produces the numerical models, the HWRF runs, the GFS runs, and the HAFS runs, and so forth. Those are the operational centers that we need to think about, what are their needs? They're the ones that make the forecast. If we're targeting forecast improvement, we probably need to be asking them what they need and seeing how we can meet those needs. Research community obviously is another stakeholder, whether it's other researchers in the government or in the academic community or even in the private sector. A lot of what we do should be serving the research community. The general public, people want to know, how strong is this storm? What's the structure look like? When are the winds going to hit us? The kinds of things that you can get from observations. So that could be another stakeholder. The private sector, whether it's, insurance companies, or it's utility companies, or, companies with oil platforms in the Gulf of Mexico. They will need to know, how strong is this storm? Where exactly is it going to go? That kind of information can be also very important. And so they can be a stakeholder. So in the case of IFEX, we identified our primary stakeholder as the operational community, where, HRD, where I came from, is a part of NOAA. The National Hurricane Center is a part of NOAA, and they're the ones that issue the forecast. And so ultimately, what we do serves the public through improving forecasts. And so the operational community was, identified as our top stakeholder. And so this is just an example from the website at HRD that talks about supporting NOAA operations. So, we explicitly lay out how it is that what we're doing is supporting the operational community. So there's a clear linkage in the case of AFEX and IFEX, for that matter, with operational needs, and that's prominently displayed. So I think that's something that needs to be thought about here as well. Second step, design an experiment that can address the needs of the stakeholders. So for example, identify what are the gaps, where are the weaknesses in prediction if you're targeting the operational community. If it's the research community, what are the gaps in understanding? If it's relevant, you can propose hypotheses. What's missing in terms of observations or understanding. Propose hypotheses to design, to test, those, or to address those gaps. And then ultimately, you need, of course, to design an experimental method. So in the case of IFEX, we identified a gap in the prediction, and that is intensity forecasting. So this was back, we started this effort in the early to mid 2000s. So if you go back and you look at the intensity and track forecast errors from the National Hurricane Center at the 48-hour time period, and you say, okay, let's go back to 1994 and let's just benchmark that to a value of 100. So let's normalize the error of track and intensity at 48 hours at 100, and let's see how that's changed over the 24-year time period shown here. So you can see that in the case of track, the green line, the track forecast errors have reduced by about 70%. If you look at intensity, it's also improved, but not nearly as much as the track. It's only been reduced by about 30%, so a little bit less than half of an error reduction in the official intensity and track forecasts. So 30% in the intensity compared to 70% for track. Now, if you actually further stratify that by rapid intensifiers, you can see that, so this is for all lead times going out to 5 days, the forecast error for cases that did not undergo rapid intensification in black and those that did undergo rapid intensification in red. Just look at the 48-hour forecast time. You can see that for rapid intensifiers, the errors are 3 times greater in intensity than what they are for non-rapid intensifiers. So the problems that we have with intensity forecasting are magnified when you have situations of rapid intensification. So that's clearly a gap in the operational forecasting community, and that's something that the observations could be used to address. So that was one of the goals underlying what IFEX was attempting to do, and AFEX for that matter, the follow-on experiment. So the next step, develop an experimental plan. So there's obviously a lot of questions, and these are just some. It's not a complete list, but these are just some of the ones that I could think of that came to mind as the most important. So first and foremost, what are the observational assets that we have available in terms of both platforms and instruments? In your plan, you need to include it's good to include a background and a motivation, certainly, hypotheses where relevant, and obviously the flight patterns that best exploit those assets. And then there's a lot of other logistics that I won't go into a lot of detail, but they're important. Who's going to handle forecasting? Who's going to decide, okay, this is what this tropical cyclone is going to do? Do we really want to get, in the case of aircraft, mobilize the resources to get out into the field, to get down to the aircraft? How likely is the storm going to be in this position, and can the planes reach it, and so forth? A lot of those kinds of questions hinge on the forecasts, and so you need to identify someone that's going to handle the forecasting for the field campaign. Who's going to make the decisions, and who's going to task the aircraft in the case of aircraft, or ground-based mobilization? Who is going to fly in the aircraft, or who's going to go out into the field in the ground? What are the areas that the aircraft can fly? Do we need to have coordination between the aircraft and the ground teams? Those kinds of questions. That's all part of the experimental plan that's being developed. So in the case of IFEX and NOAA, there's a variety, and this is not all of them, of course, but this is some of the key platforms and instruments that are used. So there's two types of aircraft: the P3 Hurricane Hunter aircraft, which directly flies through the core of the storm. There's also the G4 high altitude jet that flies in the environment at high altitude, and it can get close to the core, but it usually does not fly through the core. There's uncrewed systems. There's a small uncrewed aerial system. So, these can either be launched from the ground or from the aircraft. And there's a lot of development in this area happening right now. There's also seaborne or oceanic types of measurements. The sail drone is one example of that. In terms of instrumentation, the dropson is one of the most important instruments that are released from the aircraft. So these are sons that are released underneath the aircraft. A parachute opens, it falls to the ground. It reports temperature, pressure, humidity, and moisture back to the aircraft, which gets down to the ground. Tail Doppler radar is another very important instrument that's used on the aircraft. That gives you measurements of the winds, wind speed and direction, as well as reflectivity within the inner core in a three-dimensional sense, wherever you have scatterers. So it's a very valuable tool, both for the research, but also as has been developed in the past few years for the operations, the forecasts. And then another one is the step frequency microwave radiometer. So that's an instrument that looks down under the aircraft. It measures essentially the brightness of the ocean surface, and it allows us to infer or sense what the surface wind speed underneath the aircraft is. So that's another very important instrument that the Hurricane Center has really found to be helpful in assessing the wind speed at the surface under the aircraft. Where can the aircraft fly in the case of IFEX? So, a real advantage to what we can do in the Atlantic Basin is that the planes can pretty much deploy to a lot of different locations. So the base of the aircraft is near the coast, the west coast of Florida and Lakeland, Florida. And so what these circles are showing you, this is the P3 and this is the G4. These circles are showing you how far the range of the aircraft, assuming 2 hours that the plane can remain in the storm. So it's going to take time to get to the storm, and then you fly in the storm and do your pattern, and then you got to get back to your base. So assuming at least 2 hours, which is about the minimum amount of time that you want to have, you'd like to have more, of course. In the case of the P3, from its home base, it can fly over pretty much the entire Gulf of Mexico and the northwestern Caribbean, as well as parts of the western Atlantic. But again, a big advantage for us in the U.S. is that we can deploy to other countries. So we can go to Barbados. If you go to Barbados, you can actually get out into the central Atlantic with the P3. We've actually experimented with the idea of deploying to Cabo Verde, which is off the coast of Africa. I know the G4 has done that. I don't think the P3 has yet, but if it could, then you actually can sample easterly waves coming off of Africa and track them across the ocean. That'd be great for a Genesis kind of study, for example. So depending on where the aircraft can go, that can help to set what your priorities are and what your capabilities are as far as physical processes that could be explored. Obviously, the G4, it's a jet. It flies at a higher altitude. It goes a lot faster. It has a lot longer range, so it can cover a lot greater distance. And so based in Barbados, G4 can get even further into the central Atlantic. And, in Cabo Verde, it can actually fly over Africa and then get, pretty far west, again, into the central Atlantic. So again, it's a real big advantage for what, in the US at least, there's very few areas that the planes cannot fly, although there are some notable ones like Venezuela and Cuba and parts of Mexico. But nonetheless, everywhere else, we're pretty much able to fly. In terms of flight patterns, so these are just some standard types of flight patterns. I showed these, I think, a couple of weeks ago as well. So in the case of the P3, one very common pattern is a figure 4. So this is just an example. The numbers show just the sequence that the plane would fly. So in the case of this hurricane that's off the coast of Florida, in this example, the plane would enter from the west, fly an inbound leg west to east, outbound toward the east, and then fly downwind, and then another leg from the north to south. So you'd get 2 passes through the center of the storm. It kind of looks like a backwards figure 4, number 4. That's why we call it figure 4 in this case. Another example is a butterfly pattern. And so rather than just having 2 passes through the center, this one has 3 passes, okay? West to east, northeast to southwest, southeast to northwest. And that just gives you more looks around the storm. It allows you to get a sense of how the structure changes as you go around the storm. Looking at the G4, The G4, like I said, typically does not fly through the core of the storm, but it can fly around it. So we've designed certain types of patterns that allow the G4 to get close to the core and measure the winds with the radar on the G4, but also get dropsondes in the environment. And so an important component of the G4 are these deeper layer dropsondes. So you've got what we call a circumnavigation or a star pattern. So each of these patterns have their benefits and their drawbacks. So depending on what your goal is, what you're trying to achieve, that will allow you to say, let's fly this pattern or that pattern, or let's modify this pattern and so forth. So anyway, I won't go into the details of the text there. Don't worry about all the words here. I just want to make the point that it's important to document what your plans are, and when you design experiments, you want to, identify things like, hypotheses when they're relevant. How does what you want to do map onto whatever your longer, broader term goal is? In the case of forecast improvement for IFEX, for intensity forecasting. So clearly identify the problem, whatever the knowledge or capability gaps are, and your physical hypotheses. And then, again, how this research would advance either forecasting or monitoring or understanding. So that gets at the three main goals of IFEX. Just another continuation, don't worry about all the words here, but for this specific experiment called the vortex alignment module. So this was a module that's designed to sample a storm that was misaligned, that's perhaps becoming aligned, to try to observe and ultimately better understand those processes. And so there's a flight pattern that's been proposed for this module, this vortex alignment module, flying outbound and then flying back and forth essentially between a low and a mid-level center repeatedly. That's in the case of this module. So, provide clear instruction on the deployment requirements and the sampling patterns, distributions of expendables. Where do you want your dropsondes to be released, or your ocean probes and so forth? That should all be included in this documentation. A decision and notification process. Again, don't worry about all the words here. This is just a flow chart that talks about, each day, if there's a potential target that you want to fly, 2 days prior to that, you should start this process, right? And so in this case, there's a conference call that's internal to HRD, all the potential people, researchers that might be interested in this case, talk about, okay, here's a possible case. What do we want to do? There's a conference call with the stakeholders. So in the case of, an IFEX, the Hurricane Center and the Modeling Center are the primary stakeholders. And so we'll talk with those organizations as well as the Aircraft Operations Center. If there are collaborating experiments, whether there's an NSF experiment or an ONR experiment or what have you, we'll talk with those principal investigators to discuss potential for interactions and collaborations. There's the forecast discussion. This is obviously a very important part. So every day for the period of the experiment, which could be a few months, we'll have a forecast discussion. So someone will get up and lead a discussion for about 15 minutes, talk about the events going on. If there's a target, where's the target likely to be, and so forth. And there's discussion back and forth. And then from that, decisions are made about whether or not we're going to put the aircraft on alert for potential missions. And so, those tasking decisions, again, are ultimately made based on these forecasts and conversations. Next step, execute the plan. So obviously you want to ensure that your mission is accomplished to satisfy whether it's primarily driven by operational needs or research objectives, or maybe both. Ideally, you can design a mission that can satisfy more than one objective, but the priority in our case, at least in IFEX, is operational needs. Real-time situational awareness, what does that mean? Situational awareness just means knowing what's happening around you. And that in a very important part of that is the ability to observe what's happening and report and communicate that information, those observations, to other people in the field or on the ground. So if you can get that information to the ground in real time, that's a very important part of a successful mission. Obviously, you need to make sure that you have adequate staffing and enough crew, whether it's in the air or on the ground observing systems, as well as just people's ground support and backups in case people get sick or not, of course. And each of these people need to have clearly defined tasks and a chain of communication between the aircraft crew and the science crew. So some of the the situational awareness, the real-time products, so in the case of IFEX and NOAA, we've developed the capability to produce analyses basically in real time within about 20 minutes of completing a pass through the center. Using the tail Doppler data, for example, we can get information on things like the vorticity and, whether the storm is tilted. This is a tilt photograph or, a mission into Hurricane Milton from a couple of weeks ago. So, again, these products can be put on the web and anyone can download them anywhere within about 20 minutes of the plane completing a pass through the center. This is another example of a real-time product or near real-time product, just radius height plot of azimuthally averaged tangential winds. You can see, how small, what's the radius of maximum winds here, radius height here. How deep is the vortex? Is it aligned? Is it misaligned? How strong is it? How quickly, how small is the outer wind field? Does it extend out to a large distance or is it pretty compact? So this was a case that was, very small, 10 kilometer or so radius of maximum winds, and the hurricane force winds dropped, maybe extended about 50 kilometers outside. So it was a pretty small storm at this time. And then also things like the ability to plot the flight track in real time. And you can see the progress of the storm. If you can overlay that on a satellite image or a radar image, that's a really valuable capability. So that's something that, we've developed through collaborations within NOAA. So again, the ability to see these things in real time are really important. Adequate staffing, just from a planning perspective, if you have P3 missions every 24 hours, you need this number of people. At a minimum, you need one person on the aircraft and one person on the ground. Ideally, you'd have 2 or 3 people on the aircraft because there's multiple jobs that have to happen. If it's every 12 hours, you need to have 4 or 5 people, for back-to-back missions. So that's, it's a pretty exhausting effort if you're doing that for multiple days in a row, but, it's very important to get that temporal coverage. Again, don't worry about the words here, but, clearly defined tasks. Field program director, that's the person that's overseeing the whole program, has to make decisions on, deployments or not. What are the ultimate objectives? I don't know what the noise is in the background here. Lead project scientists, rate drops on scientists and so forth. So each of these people have clearly defined roles on the plane. And so, people can train for those and can get on the aircraft or work on the ground to make sure that the mission's accomplished. And then finally, the last step, work, after it's all done, work closely with your stakeholders to make sure that their needs are being met. So this can be done post-season and adjusted as needed. Yep. Okay. All right. Sounds good. And then the last step, work closely with your stakeholders to make sure that their needs are being met. Again, this can be done post-season after the season's over. You can adjust your efforts as needed if you identify weaknesses or areas that need to be improved. Another important part is, of course, making the data available. It's got to be quality controlled, calibrated, validated. Those are all crucial steps. And make it available to the community. That's how you serve the research community. Demonstrate the results and the value of the observations, whether that's through improving the forecasts, whether it's through advancing our understanding, publishing papers, collaborations that are developed. All of that are very important and crucial, really, to show people that are investing the money in these programs, they're getting something for their money. So again, in the case of IFEX and HRD, there's a data page that's available. It's an online, it's open to the public. The data is pretty much made shortly after missions are completed, whether it's radar data or drops on data or so forth. Logs by the lead project scientists. They'll summarize the mission as it's happening. You can get that information pretty much within a few days after a set of missions are complete. Unless it's a very active period, then it might take a little bit longer. But the goal is to get this online and out to the public as soon as possible. In terms of assessing the success, and so again, in the case of IFEX, this was, I think, a success story. So this is showing you the distribution of forecast errors, intensity forecast errors, I think at the 24-hour time period from the National Hurricane Center. So the official forecast, this is our key stakeholder, right? NHC. And so if you look at a time period from 2015 to 2017, for cases where rapid intensification were either observed or forecast, this is the distribution of the 24-hour intensity forecast error. So the median error during this period was about 20 knots, so a 20 knot under prediction of intensity when RI was either observed or predicted to occur. But there were some real major forecast busts, right? Bombs. In some cases, there was one situation where the intensity was under predicted by 75 knots, and that's at a 24-hour time period. So that's pretty bad intensity forecast. But these are very challenging cases. So that was in this 2015 to 2017 period. If you look at the 2020 to 2022 period, now you can see that that distribution has changed pretty significantly. Now the median intensity forecast error is 10, so it was reduced by 50%. And then the outlier events, so the real bombs, the worst prediction at this time was 40 knots rather than 75 knots. And so that's encouraging to see. Obviously, there's still work that needs to be done, but certainly an improvement over this earlier time period. And also, I think what's interesting to note is that there's quite a few cases where the Hurricane Center overpredicted. So, they're getting more aggressive in their intensity predictions. They're actually comfortable now explicitly predicting rapid intensification, which is kind of amazing when you think about it, because RI is such, by definition, it's an outlier event. It's an extreme event. So to predict that is, pretty amazing. Anyway, so I think this indicates substantial progress in terms of, ultimately making better intensity forecasts and rapid intensification forecasts. And to some extent, that can be attributed or credited to IFEX. Obviously, a lot of other factors went into this too, but I think the observations contributed. In terms of serving the research community, so composite data sets, I talked about this a couple weeks ago, I think, as well. So there's a database called TC Radar that includes all the tail Doppler radar analyses that have been collected for about a 25-year time period now, going back to 1997. This is actually an old graphic. It's been updated, I think, up to 2023. I think it's over 1,000 TDR analyses now from probably over 300 flights. And again, these are a wide range of intensities, not just hurricanes, but tropical storms and depressions up to Category 5 hurricanes. It's an easy to use format, NetCDF, very simple to read. And I think another really nice aspect is it's got environmental and storm metadata. So not only do you have the analyses themselves, but you've got information on how strong was the storm, what was the vertical wind shear associated with it, what was the sea surface temperature, all those kinds of all that kind of information allows you to go in and I call it slice and dice the data set. You can look at cases that are experiencing high shear versus low shear, or at a high latitude versus a low latitude, or moving quickly or moving slowly, or large or small, all those kinds of questions. You can start to answer or research that with this database. So this is just one example of the kind of graphic that you can get. This is a radius height plot of radial flow and vertical wind composites. So these are all the cases within the TCR radar database, stratified into weak systems versus a minimal hurricane versus a major hurricane. And so obviously you can see stronger inflow, stronger outflow aloft for the major hurricane, stronger upward motion in the eye wall region. So just a simple example of the kinds of diagnostics that you can do with a database like this. TC drops is another similar type of database, but now it's with the dropsondes. So these are just scatter plots of all the dropsondes stratified by storm intensity. So similar to TC Radar, it accumulates all the data from the dropsondes going back to 1996 in this case. And it's got not just data from the NOAA missions, but also Air Force and NASA, ONR, NSF, the DotStar aircraft, all not just in the Atlantic Basin, but globally. So I think it's certainly more than 30,000 drops now, because I think it's being updated. And again, similar to TC Radar, it's got the metadata. It's got the vertical shear and the SST and all those kinds of parameters associated with each dropsonde in each storm. So again, I think this is another very valuable data set that could, it's open to the research community. In terms of research productivity, So this was actually published in that 2022 article, kind of summarizing affects and transitioning to IFEX and transitioning to AFEX. But these are the number of published manuscripts that occurred between 2006 and 2020. And for all the manuscripts using IFEX data, using aircraft data during this time period. And so these are broken out into the 3 IFEX goals, which I didn't really talk about today, but one is a goal targeted toward model improvement. Another goal is goal 2 is targeted toward refining measurement technologies, observational measurement technologies. And then this goal 3 is more of a physical process understanding for processes important for intensity change. So, a total of 152 manuscripts during this time period. Most of the manuscripts are addressing IFEX goal 3, kind of the physical process research. And if you further dig into this goal 3, these 96 publications, and you stratify them into, what sort of topic are they mostly focusing on? Now, one paper can address more than one topic, so it's going to total more than 96 here. But if you just get a sense of what most of the papers were addressing, most of them looked at structure, the boundary layer, and precipitation were kind of the most important or most common, I should say, topics. But what were some of the ones that were not as well covered? Microphysics jumps out. Turbulence, environmental interactions. These were less commonly addressed in terms of the research publications. So that suggests maybe that's an area that can be focused on in the research going forward. All right, so I've talked about IFEX and the Atlantic. Can these ideas be applied in the West Pacific? Again, I'd argue that IFEX and AFEX have demonstrated a successful and sustainable path, sustainable in terms of funding, which is, obviously where a lot of this is driven by, but a sustainable path toward conducting TC field campaigns that, in this case, support operational needs, but while also giving the ability to continue to address research topics, is fundamental physical process research. So the question, of course, is could something similar be done in the West Pacific? I would say yes, obviously, or I wouldn't be here. So let's talk about how it could be adapted in the West Pacific. So let's go back to the key steps. First one, identify your stakeholders and their needs, design an experiment to address their needs, develop that plan, execute the plan, and work closely with your stakeholders to ensure that their needs are being met. So how can these steps be followed for a campaign in the West Pacific? Well, before I talk about an international campaign, let's just focus domestically on China. So first step, identify your stakeholders and their needs. Well, my question is, who are your stakeholders? So one thought would be your operational centers. Is that CMA? What are the top forecast challenges here in China? Seems like rainfall, from what I've seen and heard and talking and read, rainfall is a big threat here. Rapid intensification, that's always an issue, not just here in China, but everywhere. Storm surge, I really haven't heard a lot talked about storm surge hazards, but it seems like that would also be relevant here. Landfall hazards in urban environments, there's a lot of very large population centers, including Shanghai, right on the coast that are impacted by typhoon landfalls. So maybe hazard mitigation, maybe that should be the focus. It's not just intensity, but it's kind of like what we did with AFEX. It's the broader envelope of hazards. It's rainfall, it's storm surge, it's winds, high winds, and even severe weather at landfall. Maybe that should be the focus. What about the research community, the general public, the private sector? How can research activities be used to advance forecasting? For example, improving microphysics parameterizations for rainfall prediction. Maybe that could be an objective for a field campaign here. Second step, design an experiment to address their needs. So identify gaps in the understanding or the prediction. If rainfall is a top challenge, again, that suggests microphysics is a priority. TC track is another big priority. Obviously, the amount of rainfall in any location is a function of how long it's raining and for how hard that rain is falling. So microphysics and track are, importantly linked together for rainfall. As I showed before, microphysics was a research gap for IFEX, so maybe that could be the focus here. Landfall hazards, again, PBL structure and evolution before and during and after landfall, that's a big part. I know that there's a lot of ground-based instrumentation in China, including in urban environments. So I think that's something to take advantage of here. Again, exploit your assets and what you have here. As it's important or as it's relevant or appropriate, propose physical hypotheses and then design your experimental methods. So to develop that plan. well, what observational assets are available in terms of platforms and instruments? So these are just some. Again, there's a lot more that aren't on here. I just wanted to show one slide, but these are some of the examples, that have been used as part of Exotica and Exotica 2, and I think could be used, of course, going forward. There's a couple different crewed platforms. There's a King Air. I think several people here are going to fly a King Air mission tomorrow into Trami. Hong Kong Observatory has a Challenger aircraft. There's your manned aircraft, and then there's uncrewed systems. There's a Yilong UAV. There's seaborne types of uncrewed systems as well. And then ground-based instrumentation. I think that's a real big strength here. There's a lot of pretty extensive ground-based network, mobile as well as fixed. There's fixed towers. There's also mobile platforms, things like the Rocketsan, which can give you, high altitude drops. So design experiments that take advantage of those assets to address your needs and to address your stakeholder needs. What are the bases of the airborne and ground-based operations? This is not a complete list, but most of the ground-based locations are here in East China, including up here in Shanghai. And then the aircraft are primarily based out of Sanya on Hainan Island. The ground-based assets include, a lot of different urban locations, like I've mentioned, for example, here in Shanghai. So I think that's really good for PBL structure at landfall studies. And I know that there is already a very active area of research, both at STI and APTCRC on that. This graphic does not include other platforms like mobile and fixed Doppler. I believe China actually has a better fixed Doppler network, ground-based Doppler network than the US does. So let's take advantage of that. We can do some dual Doppler retrievals and get, wind structure. I just saw a paper yesterday that was submitted by scientists at Nanjing and NUIST that are using ground-based networks to infer eyewall structure of a landfalling typhoon. So, very encouraging to see that. Again, I mentioned the aircraft are based, in the South China Sea. So a lot of the ground-based platforms are here in the east, and the aircraft are in the south. So I'll show you in a minute here. Obviously, the area of operations for the aircraft here is in the South China Sea. So it'd be nice to be able to have a coincidence of over water sampling with the aircraft with landfall and inland sampling from the ground base. So you could actually track the evolution of the structure of the PBL, for example, of a typhoon over water, and then how does that boundary layer evolve as it moves inland, makes landfall and moves inland. So ideally, you would have coordination between the aircraft and the ground base. Now I know that there are some platforms here in Hainan Island as well, so that's good to see. I'm not sure of how extensive this network is, so I'm just learning that now, but I think that would be something that could be really valuable. In terms of, if you just look at an atlas of the tropical cyclone occurrence frequency in the West Pacific, so this axis here right along the getting into the West Pacific and into the South China Sea, these are, I guess, the typical tracks for typhoons for this 30-year time period. I mentioned that the aircraft are based in Hainan Island, and so their area of operations is in the South China Sea. So it's pretty limited, but it does include this maximum in typhoon activity. So I would say it's a limited opportunity for evolution studies for, multiple days of sampling if you can only fly in that limited area, but it does give you the ability to do structure studies, for example, like microphysics, rain band structure, and so forth. And again, I think that transition from over water to landfall and inland is a big part of what could be done here, and I think let's take advantage of that. So I do, so here's just the area again where the aircraft can operate, just to show you what I'm talking about. So a zoomed in area here shows where the Hong Kong aircraft can basically operate, and then the STI aircraft, the King Air, as well as the UAS. So, again, it's pretty limited to this region, but it just so happens that Trami is going into that region right now. So it's kind of following this climatology. So, it worked out in this case. Develop an experimental plan. So what are your observational assets available? I talked about that. Include your background and motivation, your hypotheses, flight patterns that exploit your assets, and all these other logistics that I talked about with IFEX that would apply here as well. So what I don't know, and someone can help me with this maybe, does this documentation exist right now? Has these plans kind of been made? Is there a standard sort of set of flight patterns that exist for a given research topic? If that doesn't exist, I think it should. So, execute the plan. Obviously, what is the availability of the aircraft and what are the capabilities of the aircraft? What's the plan for coordination with ground-based teams as well as with other aircraft? Is there an ability to track the mission in real time and provide products in real time? That situational awareness that I showed you examples of with IFEX. Is there sufficiently trained staff to accomplish these missions? In the case of TRAMI, this is a HWARF forecast actually of TRAMI for tomorrow morning, I believe. So this is the time I think when the mission is going to occur, and then this is 24 hours later. So this is Friday morning here and Saturday morning, and this is just a possible flight track. Now this is not what's going to happen, as I understand it, but this could be, if there was another case in the future like this, maybe this could be the type of pattern. So one thought would be the Challenger out of Hong Kong would fly a figure 4. So, TRAMI basically is emerging from the Philippines here tomorrow, organizing itself or starting to intensify. And then by Saturday, it's deepened by about 20 millibars or so. So it's now, a pretty significant typhoon as it's going to pass just south of Hainan Island. So one idea could be, well, let's get the aircraft to sample it tomorrow as it's organizing itself after emerging from the Philippines. And then let's see how that structure has changed 24 hours later. So the Hong Kong aircraft could fly this figure 4. So set up on, initial point on the west side, fly through the center, outbound to the east, and then downwind to the north, north to south, and then return to base, right? What capabilities are on the Challenger aircraft? There's no radar, as I understand it. There's no like a tail Doppler radar, but there's other instrumentation. There's dropsondes, flight level data, SFMR, I believe. So that could give information on the structure of the storm. It could allow you to, again, to sample the inner core, measure the minimum sea level pressure. You could drop sondes at the radius of maximum winds, but also at the turn points, symmetrically distributed around the storm. I think that's important for data assimilation, as well as at the center point. In addition, you can map out the wind radii in each quadrant. How far out does the hurricane or the typhoon strength winds extend? How far does the gale force winds extend out in each quadrant? And then the STI aircraft, the King Air, for example, would fly this rain band that's probably going to be on this west side. I know that there's microphysics probes on the King Air. You could fly spiral type of patterns with that to get measurements of hydrometeor profiles. How does that change in different positions along the rain band? That kind of thing. In addition, you can map out that outer core wind field on that west side of the typhoon. And again, you could do this 24 hours later. So how has that structure changed over a 24-hour time period? How well do the models in China predict that change in structure? How well do the forecasters predict those changes? That kind of thing. And then finally, work closely with your stakeholders to ensure that their needs are being met. Is there calibrated QC data available soon after the missions? Is that data transmitted to the operational centers? I don't know the answer to that question. But if they're the primary stakeholder, that seems pretty important. Have your data impact studies been performed? Can we demonstrate the value of this data to improving the forecast? Like I showed with the NHC 24-hour forecast, those histograms. Are there research papers that are being published? And are those papers tracked and publicized? Can we go back and say, 100 papers were published over a 10-year time period or something, using the data collected as part of these field campaigns? So just an example, data impact studies, I showed this a couple weeks ago too. So this is a plot going back to IFEX of the intensity forecast error, I think at across lead times for all forecasts that include the aircraft data in the black and then that do not include any aircraft data. So basically just look at the black line, and this is forecast improvement for positive numbers, intensity forecast improvement. You can see that forecasts that included aircraft data had about, close to a 15% improvement at the 48-hour time period when aircraft data were included compared to when it was not included. So that shows a measurable impact in terms of improving the forecast. And again, track your research productivity. How many papers are being published and what areas are they focusing on? That can help to sort of guide perhaps future efforts going forward and prioritize. So with that in mind, I had some thoughts on a possible field project and motivation going forward. So it's building upon what Exotica has done successfully, I'd say, for the past 10 years or so. But going forward, perhaps trying to work closely with stakeholders to demonstrate value for whatever they need. And so my thought was, a goal could be to improve typhoon hazard prediction and mitigation. So, whether it's rainfall or it's rapid intensification or storm surge or what have you, these are all, boundary layer and damage, in an urban environment with a landfalling typhoon. All of these types of situations are what data that could be collected here could help to improve. So let's, improve the prediction and the mitigation through a combination of activities. The first activity would be an improvement in the typhoon analyses and forecasts. The second activity, major activity, would be developing and refining observing technologies and strategies for typhoon monitoring. And then finally, the third one is better understanding the physical mechanisms that govern typhoon hazard structure and evolution. So as an example, that first activity, the improvement of typhoon analyses and forecasts, could include numerical model evaluation and improvement. That's a really important part. The data that would be collected here in the West Pacific could be compared with whatever the models that are run locally are producing to see what are the weaknesses and how can they be improved. Data assimilation, that's a huge part. A lot of the forecast improvement in the Atlantic has been driven by the availability of intercore data from the tail Doppler radar, and that data is assimilated into the HWRF and HAFS models to make better 24 to 48 hour forecasts based on that data. AI-based analysis and forecast tools, that's a really emerging area that's really become quite popular and extensive. So that's another technology that should be taken advantage of. Database development and maintenance. So whatever data is collected, let's put this out for the public and let's maintain, let's continue to expand on this data and add to it, and not just aircraft data, but satellite data, ground-based data, ocean data, and so forth. I've seen a lot of nice examples of that already. Storm Hub, I think it's called. So that could be continued and built upon. That second objective, or that second activity, developing and refining observing technologies and strategies for typhoon monitoring. So the development of real-time situational awareness tools and products. And I think it's important to have these real-time products not just available for the research community, but also for the forecasters. And it has to be put into their, in front of them when they're making the forecast. This is what the plane is showing you. This is what, the ground-based radar is showing you. This is how strong the storm is, and so forth. And they can use that to make better short-term forecasts. Again, it doesn't just include aircraft data. It includes satellite data, includes, ocean data, as well as ground-based platforms. And obviously, calibration and validation activities are very important in this as well. And I mentioned observing technologies, but also strategies for typhoon monitoring. So this can include things like targeted observations. Where can we best release dropsondes, for example, to optimize a forecast of track or intensity or structure? Those types of activities. Observing system simulation experiments. If we want to invest in a new technology, where is it? How much of an improvement in the forecast is that likely to produce? That can really help in for decision makers to decide how much money to invest in a certain observing technology, for example. And then finally, that third and final activity, which I think is also very important, it's improving our understanding of the physical mechanisms that can govern typhoon hazard structure and evolution. So this is just some of the areas that I think we could be focused on. Mesoscalar vortex structure and dynamics. Whether it's secondary eye wall formation or vortex alignment processes or what have you. Precipitation processes and microphysics. I've talked about that certainly quite a bit in terms of microphysics, as well as the next one, turbulence and boundary layer, and the boundary layer structure and evolution. Air-sea interaction, I didn't talk a lot about that, but that's obviously very crucial in terms of likelihood for intensification. Environmental interactions, that was a gap in the research activities from the IFEX papers. Trough interactions and vertical shear, intensification and moderate shear, those types of things. Those are other important areas. And these all play varying roles in the typhoon hazards, whether it's RI or the winds or rainfall or storm surge, but they all obviously play an important role and would be certainly important areas to research. Finally, I'll just say APTCRC is hiring. So, we're looking for talented and motivated researchers to help us advance our efforts toward improved understanding and prediction of typhoons that can protect life and property worldwide. So if you're interested, you can contact me and be happy to talk to you about opportunities. And with that, I'll just say thank you and take any questions.
Yeah, thank you, Rob, very much for your excellent talk about how we organize typhoon observation campaigns and our future plans. So have any questions or comments? So I think firstly, we can open for the online participants because there are some participants yet online. Is there any questions for the online guests or experts? Yeah, there are some questions.
I don't want to mess something up.
Sorry. Yeah.
I think it might have been.
在哪里
I think it's that.
Here. Yeah.
I'll go to the top, I guess, or just
No,
okay.
this is the first one.
Okay. Okay, so it's known that HWRF or maybe HAS made the best TC forecast now. How can we make full use of the observation to make a better initial field, to use them in DA or TC dynamic initialization? Yeah, so so I mentioned DA, I think is a really important part of making better forecasts. I'm not an expert on these issues, so I can't speak to dynamic initialization versus DA. I do know that there has been quite a bit of effort in the U.S. at HRD on improving the data assimilation techniques, on solving Kalman filters and particle filters and things like that. I will say that in terms of the observations part, the studies that I've seen and the data impact studies that I've seen have found that probably one of the most important contributors to making better intensity forecasts is the radar, the tail Doppler radar, especially for weak systems. Not so much for the strong hurricanes, but these weak systems are the ones where if you have a numerical model that does not have any observations or not any data assimilation, it tends to assume that it's just an aligned upright vortex of a given intensity, right? So there's a certain assumptions on the initial structure. But a lot of times these vortices can be disorganized, they can be misaligned, shallow and so forth. So those assumptions that go into those initial conditions sometimes aren't valid. And so you need those observations that can effectively get into the model, whether it's through DA or dynamic initialization. If you can accurately represent those initial structures, then the subsequent forecast ends up being better. And I would say not only is that information important for the models, but it's also gotten a lot of interest in the past few years by the forecasters at the Hurricane Center. So they actually use that information in real time to assess, is this vortex aligned or misaligned? And so they can, based on, this is why it's important to develop these situational awareness tools and products that can be transmitted in real time and get to the forecasters so that they can know this vortex is not likely to intensify in the next 6 or 12 hours. It's still struggling with dry air or it's misaligned. So the tail Doppler radar has been really shown to be really important in terms of the intensity forecasts, not just for the models, but also for the forecasters. Okay. Thank you. Do you have any plans of TC Genesis campaign? Yeah, that's a great question. Certainly in the Atlantic, that's been on our books for 20 years, 25 years. It's very hard to do a Genesis in the Atlantic, at least, and I'm sure elsewhere. And a lot of that is just honestly for logistical reasons. You have to make forecasts, you have to deploy the aircraft. And so if the thing about Genesis is it's very uncertain. And so it requires a lot of faith, basically, to, in the models. If the models are suggesting that something may be developing, but it may not, it's a lot of resources to get down to Barbados, for example, and you have to know that many days out in advance. And so a lot of times we just end up hesitating and waiting until it's too late. And so by the time we get the planes down there, it's already undergone Genesis. So we sort of became convinced that to effectively do a Genesis experiment, you just have to go into the field and we're going to sit there for a month and we're going to fly waves as they move across. But that costs a lot of money. So we haven't done that yet. Now in the West Pacific, let me go back to can I do this? Not messing anything up? Let me go back to this plot. This one. I'm actually going to kind of talk about this. How do I get to the full screen? Is that the play? Okay. Thanks. Yeah, so this is the area of operations for the aircraft, at least in China, right? So, you know, a lot of the genesis, I think, happens probably out here, right? So you would need to deploy. So where are we going to deploy? So I think this argues for the importance of an international field campaign. I know that the Japanese have a G4. I think the range of the G4 might be somewhere down into here. Koreans have a King Air. I know, and you know, Taiwanese have a Dot Star. So, you know, if we can work with some of these international partners and design an international campaign, there could be perhaps opportunities for these aircraft to get further out into Genesis locations, and then, you know, perhaps let's say that there's a typhoon that's going to develop here in the southwestern West Pacific, let's say. And then track into the South China Sea. Maybe some of these aircraft could track the Genesis when it's out over the open water here before it reaches the Philippines, and then as it gets into the South China Sea, maybe you know, the Challenger and the STI King Air aircraft could pick that up as it gets into the South China Sea. I mean, I could envision, you know, a dream scenario would be internationally sampling this system as it undergoes Genesis, and then monitor it and track it as it's moving across and continue flying it, and then pick it up as it undergoes rapid intensification, either just before or just after emerging from the Philippines and the South China Sea, and then it comes inland. So you're getting Genesis, you know, rapid intensification, mature stage, landfall, post-landfall in China. You know, that would be, in terms of a sampling, a kind of a dream scenario. But there's a, you know, a lot of challenges to that, you know, a lot of discussions that have to happen, but, you know, that would be, I think, something that could be a great data set. I think I've lost. Yeah, so I don't know if there's any other questions. How do I get back to that here? Think, right? Okay, yeah, no problem. Any other questions?
Have any other questions online? If no, we will turn back to the S slide. Yeah. So do you have any questions or comments here?
Yeah, Rob, I think that's a very good planning and good introduction to what you had done in the HRD. But I think if you say you have prepared a proposal, I think you can include some cross validation with satellite observation. Yeah. That's probably enhance your proposal here in China in particular. Yeah. Because we have foreign satellite. Yep. They can also just focus on one storm. They can tune, you know, the angles of the satellite. Right. And then can simultaneously observe the one storm, and then you can have to see the satellite data, whether any correction you need for the
I mentioned it somewhere. Just trying to find it. Yeah, I mean, I certainly agree, and you know, my focus here was mostly on the aircraft, just because that's my experience, and the ground-based on some sense, but I know that the satellite and the work that's done with the spaceborne platforms here, out of necessity, I think it's much more prevalent, you know. So that's another area that we have to leverage. And I think honestly at HRD, that was a weakness. There wasn't really a strength in the satellite. It was all focused on aircraft. So I would want to take advantage of the expertise in the satellite analysis and the potential for validation and intercomparison with the aircraft data, for example, and optimizing your satellite sampling, right? So I think that's certainly an important activity that would be part of this proposal as well. That could be in that second goal, perhaps, right? The development, refining, observing technologies and strategies for monitoring. So, and I mentioned it includes spaceborne, air, seaborne, and ground-based, and how they interact with each other. That's the validation activity, right? So I agree, certainly.
I think that's can leverage.
Yeah, leverage the strengths, right?
Yeah.
Yeah.
Have any other questions? Yeah.
My name is Wan Zhengwu. I'm one of the guys doing the microphysics parameterization.
Great.
Yes. For a while, we have been thinking how to improve the TC intensity forecast through the microphysics parameterization. And we conducted several sensitivity experiments And we also proposed hypotheses about the condensation or some assumptions in warm rain process or ice processes. And we saw the differences in our experiments. And those differences are usually lower than our expectation, or sometimes totally opposite to our expectation. So that leaves us a difficult situation that it is hard to identify the gaps or propose the hypothesis in the intensity improvement. So many times I keep questioning myself that is the microphysics really a key in improving the intensity forecast? So I'm wondering that maybe we are not thinking in the right direction, or how to like realize or understand the situation we are. So I'm not sure if you have any suggestion.
Yeah, no, I feel your pain. I can understand the frustration. Honestly, in terms of intensity forecasting, I'm not convinced that microphysics is a key player as well. You think it would be, because microphysics should determine where your heating profiles are and how they're distributed spatially and temporally. But yeah, I'm not honestly surprised to hear that you're not seeing a significant impact. I do think it could play an important role in rainfall. So again, that's where I think it's better to look beyond just intensity, but look at the hazards, right? So intensity is part of that and rapid intensification, but the rainfall is a big one too. So to what extent is the rainfall accumulation sensitive to your microphysics? And then in terms of the observations, it's great that you're here, and I'm glad, thank you for asking your question, because I think this is an important step. It's that dialogue between the observationalists and the modelers. How can observations help you? Based on what we can collect with the probe data on the King Air, for example, would it help you to get distributions of liquid water and even ice in certain locations? And can you compare that with what the model is saying to say, okay, well, it looks like the model is handling this well, or it's not handling that well. Can the data that we could provide you help you in that model development? So that's that first goal, right? So that's how the observations could help with the models. And so that's something that I think should be at least one emphasis in our activities here. So it's great to have this dialogue, and I think that this should continue. Absolutely. I mean, that you're an important stakeholder in terms of the model community. And so, so thank you.
The ACR.
Oh, APTCRC?
Yes, so
Great.
I think we can work closely in
Awesome.
the future.
Yeah.
Yeah, last time she went to Europe. That one.
Oh, okay. Yeah. So you were in Europe when I was there a few weeks ago.
Yeah.
Yes.
Yeah,
Gotcha.
you missed our meeting.
Yeah. Gotcha. Portugal. Nice. Okay.
Yeah. Okay, have any other more?
Hi, Rob. Thank you for your interesting talk.
Thank you.
I just have a small question. Are flying into a strong type TC more challenging than flying into weaker tropical cyclones?
Define challenging, I guess would be my question. That's a good question. In some ways, I would say that a weak TC is more challenging for a few different reasons. One is that they're less organized, so it's harder to know exactly where to go, honestly. Like if you're trying to target the center, you might not know where the center is. If it's a weak TC, if it's misaligned or broad vortex. Also, a lot of times these weaker TCs have isolated strong convective cells, whereas a stronger typhoon is a little bit more organized in that sense. And so you kind of know where you're headed and what to expect. Now, that being said, some of the nastiest bumps I've ever encountered are in these rapidly intensifying Category 4 hurricanes undergoing an eye wall replacement cycle, right? So you get these mesovortices on the inner edge of the eye wall. You can get some really nasty bumps and crazy movement of the plane that you don't typically see in the weaker system. So in terms of the turbulence, I think it's probably worse at the altitudes that the P3 flies for the stronger systems that are intensifying. But in terms of the challenge and the logistics, it's harder, I think, for a weaker system. So they both are difficult for different reasons.
I have a question. You mentioned now we have not made any more research about the environmental interaction based on the campaign.
Yeah,
And
and IFEX, yeah.
it that means that you have to have a larger area campaign or observation because the environment, I don't know, but I'm just curious how to do that if we want to do more research about the environmental interaction
Yeah, yeah.
of between the tropical cyclones and also some like trough or
Yep.
so.
No, that's a good question.
Yeah, thank you.
I think, yeah, that argues for the capability of like a multi-plane mission, right? So in the US, we've got the G4, which samples the environment, and then you've got the P3. So the P3 is kind of the inner core aircraft, and then the G4 is the environmental aircraft. So that gives you the ability to sample the environment, things like an upper level trough. Here, I'm not sure what, other than this is why an international campaign would be great, because Japan has the G4, right? So they could sample, I know they like to fly over, they like to fly over top of the eye, but if they could also sample the environment, then you can get information on that, or, other aircraft like that. I don't know the UAV, I don't know, this is why I need to know the capabilities better, how high that could fly or how long that could fly. So maybe that, like in the US, there was a Global Hawk that was used for a few years that flew even higher than the G4, like in the 20,000 feet higher, 60,000 feet or something, that could stay aloft for 24 hours, right? So you could really map out the large scale environment. Obviously, you also have global model analyses and that kind of thing. So that's also a way that you could merge, kind of global analyses with the inner core data. So in the absence of the aircraft at high levels in the environment, you also have the analyses. So that could be something that, could be used. And, you want to look at things like ventilation, right? Dry air up shear, is that getting into the inner core? Those kinds of things that you could sample with dropsondes, or perhaps just rely on the global analyses. But I think if you had the ability to get the data from the aircraft, you'd want to use it. So anyway,
yeah.
A multi-plane mission, high altitude environmental versus inner core, I think is the ideal if we could get that.
Yeah. Thank you.
Sure.
Hello, Dr. Rogers.
Hi.
My name is Xianming Chang.
Uh-huh.
Okay, and I think I have taken part in several times in the observation campaign in STI.
Great.
And I think your talk today will improve the design of our observations. My question is about the instrument.
Mm-hmm.
If we have we know that let's take the wind LiDAR, for example. In China, we have, for example, 5 or 10 companies can produce the wind LiDAR. So in one typhoon campaign, if we have 2 companies of this product, so do you prefer to use just one Doppler LiDAR from just one company, because the data quality may be very stable, or you prefer to use different of LiDARs that the 2 LiDARs are from 2 different companies, because the advantages is you can cross validate the data quality from those 2 companies.
Mm-hmm.
So my questions.
Yeah.
Do you understand my question?
Yeah, I do. Yeah,
Okay.
I'm just trying to think of it. I think you'd want to keep your options open as much as you can. If you've got 2 competing companies, let's say, with LiDARs, like what are the differences, right? What cost is certainly one, I would think, but also capability and stability and, how well validated can you intercompare? The thing about, so are you talking ground-based or like an airborne LiDAR?
Air and ground-based.
Ground-based, yeah. So yeah, that gives you more options. If it's on the aircraft, then there's limited space on the plane, right? So you might have to make a decision. But on the ground, I'm assuming, yeah, you can have, as long as you can afford it, I would think you'd want to have more than one option, right? If it comes down to it, though, then you've got to decide, what are the factors, and I can't give you that right now. And I don't know a lot about the LiDARs. I would rely on people with the expertise to tell me what, is the best way to go. But if you could, I would say keep your options open, right? And have multiple different capabilities to intercompare and let competition work, right? So that's the other thing.
Okay, thank you for advice.
Yeah, thanks.
Hi, Rob. Thanks
Hi.
for a very nice lecture.
Thank you.
Thanks for sharing us all this knowledge. But I'm quite surprised to see that you have so many stakeholders, because I was wondering, because the stakeholders may have conflict, multiple plans and their aims and goals. So when you're like designing an experiment for them, right? You need to make sure that your personal, sorry, not the personal, the project goal for that. And then you told us that you develop an experimental plan based on what observational assets are available. Yeah. So I'm wondering if, like, for example, if two scientists or one scientist and another forecaster are both your stakeholders, and they definitely have different needs, right?
Yeah, right.
So then from my personal understanding, it's like, for example, if I have only one stakeholder, say like a researcher, and he will provide me the budget to buy the specific assets, the observation apparatus on my plan so that I can do the observations. But according to your lecture, I don't know if it's like, so first we check how many available assets we have and how many data we can collect, and then to see how we can serve them based on the things we already have. Not like we submit a budget and then they will give us some money and then we can buy some new instruments so that we can have new observations.
Yeah, so in the US, I mean, yeah, what you're describing in terms of like competing interests, I mean, that's field campaign work, right? So, I've heard stories about people coming to fight each other, right? Literally fighting each other because one person wanted to fly down low and the other person wanted to fly up high. That kind of, so that's on the research side, the stories that I'm thinking of. But I listed a bunch of stakeholders, and I'm not saying that they all have to be stakeholders. These are just possible stakeholders. And the other thing I would say is, you have to set priorities, right? So your highest priority, I would say, is the operational. At least in the U.S., it's the operational forecasters, right? Because that's NOAA's mission is prediction ultimately, and so all of what is done on the research side in NOAA is to support that mission. So if there is a choice between we need to fly this pattern to address the Hurricane Center and what they want, or this researcher that wants us to do this different pattern, we're going to do the Hurricane Center, right? Because that's a priority. And so it's important to have someone that's in charge that can make that decision and set those priorities. Now, if it comes down to researcher versus researcher, that's when you got to have some negotiation, perhaps, and a director that is willing to kind of say, okay, this is what we need to do. Maybe you can take turns. Maybe one time you can address that person's interests, and the other time it's the other person's interests. Now, in terms of the assets are what they are. At least in the U.S., we have the aircraft every year. It's not like we get different aircraft different years, of course. The instrumentation even is pretty much like the standard instrumentation that I've been showing you, the radar and the dropsondes, that's always there. Sometimes instrument PIs will come on and say, we are interested in getting this instrument on the plane this year. And if they've got the funding and there's the space, then they can do it. And so again, this comes back to what the field program director makes these kinds of decisions. Like, what's the priority this year? Would this instrument help us with what we want to do scientifically? Or do I see a way that this could maybe help the forecasters? Again, that's the stakeholder addressing part. So yeah, you need to set the priorities, of course. And you need to have a director that's able to make that decision and know what those priorities are and execute on those. Okay.
Great, thank you.
Sure.
Professor Robert?
Yes.
How are you? Okay. I'm Kujin Huang. I come from the Guangzhou Institute of Tropical and Marine Meteorology.
Okay.
So you do a very good introduction for the field campaigns.
Thank you.
We all know that typhoon energy most comes from the ocean.
Right.
So the ARC interaction is very important. Yeah.
Yes.
Include energy transportation, spray effects, and ARC flashes, etc. So now many observations using the several gliders and the buoys. So do you have any suggestion about this side observation suggestions?
Yeah, I mean, I didn't talk about that a lot, but absolutely, I agree that that's an important part of this, especially in terms of intensity change processes, but also maybe even structure change. Let me see if I can, I don't really think I have much here to refer back to, but yeah, no, I would say maybe this. Yeah, so certainly the ocean sampling capabilities, so like that, I talked about these 3 goals perhaps for a potential West Pacific campaign. That second one, really all of them. So well, I was going to say the second one, we're defining and refining, developing and refining observing technologies and strategies for typhoon monitoring. Certainly, the observational platforms that I've been talking about, the aircraft, the ground-based, and the ocean observing systems are very important. I know in the U.S. we also have gliders that are used. We have the sail drones. We've got a variety of buoys, moored buoys, and deployed buoys, and so forth. That they're folded into our field campaign too. They're certainly an important part of the observing system. So it's really a fully 3 or 4 dimensional, if you will, three-dimensional in the sense of sub-ocean surface up to the ocean surface, the air-sea interface, and then the atmosphere up to the the tropopause. Full depth of the ocean and atmospheric system that is really the optimal kind of data set that we could provide. So to the extent that we could combine these ocean observing systems that you're describing with the atmospheric observing systems that we would try to provide with the aircraft would be wonderful. You'd want to perhaps, I don't know if there's an ability to deploy ocean buoys from the aircraft. I don't think there is, but if there were, like in the US, a lot of times we'll release dropsondes at the same time that we release an ocean, a AXBT, right? That gives us sea surface temperature and subsurface temperature structure. So you from that you can estimate fluxes, right? So those kinds of sampling strategies would be something that I think we'd want to do here if we could. So yeah, absolutely, the ocean observing systems are a key part of this kind of holistic field campaign.
Okay, thank you.
Sure, thank you. Yeah.
Okay, thanks, Robert. In fact, in the West Pacific severe rainfall disasters are more frequency. For example, relatively weak cyclones caused severe rainfall events. So could you give some suggestions on the TC precipitation campaign?
Yeah, well, so that gets again at the whole hazard part of this, right? So it's not just intensity, of course, and rainfall is a very important hazard, and I know in China in particular, it plays a significant role. And it's not just associated with the typhoon; it's these remote rainfall events, right? So it gets at the importance of the ground-based network and not just at the coast, but far inland, right? So rain gauge networks, radar networks, disdrometers. Those kinds of measurements, I think, are really important. I don't think you can't get the microphysics kind of measurements from the aircraft over land, but there are dual pole capabilities, I believe, right? And I think, right, in the ground-based network, are they polarimetric? I think they are. I know Kun Zhao has shown me some results from analyses he's done. So and I think that's been used here. So again, that's another. Again, I didn't talk about it here, but yeah, there's a whole wealth of observational capabilities. And I do feel like, at least maybe my experience in the US was limited on the landfall side, but it seems like in China there's a stronger effort in terms of the landfall measurements and the inland measurements to link that with a typhoon landfall. And so we just need to get the offshore part, I think, better. I think in the US our strength was over the water with the aircraft because that's our experience, and less so post landfall. I think in China it's landfall and post landfall. So now let's work on the over water. But yeah, I think in terms of what I mentioned, in terms of the observing capabilities, the rain gauge network, the radar network, perhaps dual pole capabilities, those all can play a role in refining microphysical parameterizations, for example.
Thank you.
Sure.
Have any more questions? Yeah.
Thank you, Dr. Robert. My name is Xinyan Zhang, and I'm also very interested in using aircraft observation to do some research and look into the TC structure and so on. But I'm not quite sure that, as you introduced before, there are there are different flat patterns, and I think sometimes we will get a more data set for a storm case, and sometimes the data is less. And I'm not sure if the data quality also varies by different storm cases. So can we just compensate all available data, or how can we select the right observation experiments for our research? So that's my question. Thank you.
So your question is, how do we, yeah, so yeah, I mean, I guess you're going to, yeah, not all typhoons are going to be the same, of course. You know, some structures are going to be different. Some of them are going to be asymmetric. Like in the case of radar, right, on the plane in the U.S. If you have a hurricane that have a lot of scatterers, it's very symmetric. You're going to get great radar coverage in that case. But there might be other cases where there's not a lot of scatterers on one side of the storm, and so you can't see what the winds look like on that side because you don't have scatterers. And so I think, you know, if I'm understanding you right, I think this argues, you know, like not every mission is going to be as successful as another mission in terms of the data that you collect. Obviously, some of that's you're going to be limited by how far the storm is from your base. You know, how much time can you spend in the storm? If it's really far, you might only get like one pass through the center. Whereas if it's close, you can do multiple passes at different locations, so you can get a real nice picture. So I think that, you know, in the US, we've been doing this for, you know, 60, 70 years, right? And so with some of our more modern instruments, maybe 30 years. So we've built up this large database. This is why the value of something like a TC radar comes in, right? Or TC drops. So I think if we can build a database here of many different typhoon missions, then you can start to look at, okay, not every case is going to be great, but some are going to be good. And if we have enough of these, we can composite them together and look at kind of mean structures of typhoons for ones that are intensifying versus ones that aren't, or, you know, what is the microphysics? If we're getting enough of the microphysics data, we can sort of get, okay, this is what the profile looks like on the downshear side versus the upshear side, you know, those kinds of questions. So I think, you know, building a statistically robust data set through many different missions, I think, is an important part of this. And so that requires sustained support for resources to do these missions over time. And so I think if you can do that, then some of the missions that aren't as successful in terms of the data quality are mitigated. There's not as much of an issue. So I don't know, did that answer your question or?
Thank you very much.
Okay, thank you.
Very impressive talk. I have one question about the operational use of the observation. So how do you use the observation to improve the forecast based on data simulation? Because it's very important for the landfall typhoon if we use them in the forecast before it makes landfall. How do you decide what kind of data to be used for operational use?
So yeah, in terms of data simulation in the US, it's largely kind of all the data now. I mean, they've developed these data simulation schemes that can incorporate not just the flight level data, but the dropsonde data, and now the radar data and the SFMR data. So all of that is getting into the data simulation system. What it does argue for is the importance of the data assimilation system. You need a system that can sufficiently incorporate that data. And so what I don't know about here is the data assimilation systems that are here. So, you know, this is why it's important to have this dialogue with the modeling and the DA communities to know what data is missing, what data do they need. You know, as far as how do the observations improve the forecast, I think that the data assimilation is one of the most important ways that the observations can help. But I also would say that the evaluation work is important. I didn't talk about it here. I talked about it a couple of weeks ago. But, you know, we've been able to use the observations to improve things like the formulation of mixing in the vertical to get better boundary layer structures in the model based on the observations. So maybe we can do a similar thing with microphysics and rainfall and maybe even intensity change. Those types of activities, I think that first goal that I talked about here, improvement of typhoon analyses and forecasts, right? So those are both really important activities, and those require, I think, that strong communication between what we want to do as observationalists and what the modeling community and the data assimilation community needs to make better forecasts. Okay. Sure.
Yes. If no, I think 没有. Okay. No questions anymore. So I think it's very good lecture. And thank you again for Rob give us a lecture. And thank all online participants and outside participants to join us to discuss. Very excellent talk. So thank you very much.
Okay. Thank you.